Hello, welcome to the review for the final quiz. So the main topics for the quiz and also just kind of this part of the quarter is angular momentum, energy, and universal gravitation. I'm just going to quickly go through these slides. Again, these slides are just mainly for you to reference. And then I have some examples I'm going to do at the end. But angular momentum with the right hand rule, if you have linear momentum information, you can use the right hand rule for the cross product. But if all you have is the angular velocity, you just curl your fingers in the direction of that rotation. So rotation about a fixed axis. Then there's the example of precession, where we're rotating counterclockwise. So our angular velocity, our angular velocity is pointed up, but so is our angular momentum. And then we have forces acting on the axle. And so we can use the right hand rule for torque there, where your fingers go in the direction of where the force is applied, and then the fingers curl in the direction of the force, and then the torque is in the direction of your thumb. So here the torque is in the positive y direction. And so our angular momentum is in positive L, our torque is in positive, our angular momentum is in positive Z, and our torque is in positive Y. So it's going to precess toward the direction of the torque, or toward that positive Y axis. It's going to start to tilt that direction. That's a reminder of precession. And then work is usually the force times the distance times cosine of the angle. But depending on how it's presented to you, what you want is the component of the force that's in the direction of the motion. So if this force was instead along the plane, it would be the whole force, but here it is only the cosine component because that's the only component that is parallel to the plane. Kinetic energy is 1/2 mass times the velocity squared, and work is equal to the change in kinetic energy. Then potential energy, work is equal to the negative change in potential energy. And what this looks like depends on what is causing the potential energy. Skipping through the animations. So for a spring, it's 1/2 kx squared, where k is the spring constant and x is the displacement from the resting length of the spring. And then for gravity, it's mgy, just y being the height from the ground. So work is equal to both the negative change in potential energy and the positive change in kinetic energy, implying that the change in kinetic energy is negative the change in potential energy. And we talked about the concept of conservation of energy, where if we're in an isolated system with only conservative forces, the total mechanical energy remains constant, which is just the sum of all the energy. And we can use this to solve for different variables in different situations, because the initial energy equals the final energy, which means the sum of kinetic and potential initially equals the sum of kinetic and potential in the final situation. And as a reminder, this doesn't mean that the potential energy is constant, but it means if the potential energy increases, then the kinetic energy must have decreased, or vice versa. And then we have kinetic energy for rolling motion. You're not really going to have to refer to the work done in rolling motion or the power. The kinetic energy is the important part. This is rotational kinetic energy. And then remember, rolling motion combines translational and rotational. And the main point here is to get you to this, where if something is rolling, then your kinetic energy is a combination of that rotational motion and then the linear motion of the center of mass. So if something is rolling, your terms are 1/2 the rotational inertia about the center of mass times the angular velocity squared plus 1/2 the total mass times the velocity of the center of mass squared. Then for energy in systems, it was just that, well, it depends on how you define your system, but in general, the changes in energy of the system are equal to the external work applied to the system. Then Newton's law of universal gravitation, where the force is G, which is a gravitational constant, times the mass of each object times each other, divided by the distance between them squared. And this is an attractive force, so it always points toward the other object. So that means if you're moving away from the object, work done is going to be negative. And reminder also on the principle of superposition, where if we're looking, for example, here at the gravitational forces that the Earth experiences from the moon and the sun, we can think of them each individually. So we can say, okay, pretend the sun doesn't exist. What is the gravitational force on the Earth from the moon? And then pretend the moon doesn't exist and do the same thing on the Earth from the sun. And then you can just sum those vectors up to get the total gravitational energy or total gravitational force experienced by the Earth. And near the Earth's surface, the main thing here is this is where our acceleration due to gravity or free fall acceleration comes from this universal gravitation equation, and it is the gravitational constant times the mass of the Earth divided by the distance from the Earth squared. So for close to the Earth's surface, so like radius of the Earth is what this R would be, then we get like that 9.8. But if we get farther away, it changes. And then gravitational potential energy, if this is like for universal gravitation, is negative GMM over R. And this negative sign comes from the fact that it is an attractive force. And so it's important to remember the negative sign here because it can really mess things up if you're trying to use this without the negative sign. There is the escape speed, which is the speed needed for an object to escape the gravitational pull of another object. This comes from conservation of energy again. But you can also refer to this equation, which is square root of 2gm over r, where m is the mass of the object you're trying to escape from. Then just a quick review since this was very recent. So Kepler's first law is the law of orbits, where all planets move in elliptical orbits with the sun at one focus. Kepler's second law is the law of areas, where a line joining any planet to the sun sweeps out equal area in equal time. And Kepler's third law, which is the law of periods, says the square of the period of any planet about the sun is proportional to the cube of the planet's mean distance from the sun, or the period squared is proportional to the distance cubed. Okay. Ooh, we did it. We made it through the lecture part. And now let's do those examples. So, examples. I'm not gonna, they're in the slides, but I'm just gonna go over to doing them and I'll read them to you there. Okay, so the first question comes from the Weekgate practice. It's question 2, which is from chapter 11, exercise 1. So to push a 52 kilogram crate across the floor, a worker applies a force of 190 newtons directed 22 degrees below the horizontal. As the crate moves 3.3 meters, how much work is done on the crate by A, the worker, B, the force of gravity, C, the normal force of the floor on the crate, and D, the friction force. And this is my bad, I didn't change this here, so it should say the friction force of, let me check, what did I change it to? 125 newtons. Okay. So let's start with just a drawing. Also, oh, I added part D. It wasn't in the homework or the practice. Just because I wanted to include friction. So here's our pushing force. It's kind of pointed down, but we'll draw our free body diagram so that we can see the forces better. So here's that pushing force from the worker. Here's the angle theta, and then we have our normal force going up, our weight force going down, and that kinetic friction force going opposite the direction of motion. Okay. Then part A asks for the work done by the pushing force, work by pushing force. And so for this, we want the parallel component of the force. So the motion is just along the floor. So we want the component of the force in the positive x direction, which we'll say that is the parallel component, which is just the pushing force times cosine of the angle because it is the side that's adjacent. So the work done by the pushing force is the parallel component times the distance, or the pushing force times cosine of 22 degrees times the 3.3 meters. And here the pushing force is 190 newtons. Sorry, I didn't write it there. So for this, for the work from the pushing force, we get 581 joules. Then it asks for the work done by gravity. Yeah. Work by gravity. For this, our motion is in the horizontal direction. The force of gravity acts in the vertical direction. So there's no motion in the direction of the force of gravity. So the work done is 0. Work by gravity equals 0. No motion. Also, or you in that direction, or we could say that the force is perpendicular to the motion. So, which is that's saying the same thing. And then for C, we're asked for it for the normal force, which is again the same thing because the normal force points up instead, but our motion is just horizontal. So work by normal force equals 0. Joules. Just keep our units even if it's 0. And finally, for this one, work done by the friction force. So now the friction force is along that same horizontal direction, but it is pointing in the opposite direction of the motion. So, but all of it is pointing in the horizontal plane. So we don't have to do like cosine or anything, but we have a negative. So work by friction equals negative friction force times that distance. Negative 125 newtons times 3.3 meters gives us a work from the friction force of negative 412.5 joules. Okay, so just a quick review of this. We drew our free body diagram, which was really helpful because we referred to it when thinking about the motion, the direction of the motion and the direction of our forces. And we found that the vertical forces didn't do any work because the motion was not in that direction. Next up, this is from the week 10 lecture 1 application. I think that it was the only problem in the application, so I guess you could call it number 1, but it didn't have a number. So we have a small solid spherical ball at the top of a 4.2 meter hill. After coming down, it rolls up a 5.9 meter hill. What initial velocity does the ball need to have at the top of the first hill to just make it to the top of the second hill? So, first thing is this is a small solid spherical ball. So, and it's rolling, it's a ball. So let's get the rotational inertia of a sphere, and that is 2/5 mr squared. Okay, now we'll do our conservation of energy, where kinetic energy initial plus our potential initial equals our final kinetic and final potential. But we're looking for the minimum initial velocity here, and we know this because what this is. What initial velocity does the ball need to have at the top of the first hill to just make it to the top of the second hill, which tells us that final velocity is 0, so the final kinetic energy is 0. So let's write these out and remember that kinetic energy for rolling motion is 1/2 I omega squared plus 1/2 mv squared. So I just wrote it, but I'll write it again. I omega squared plus 1/2 mv squared equals, oops. Then we have the potential energy here, so that's mgh1. And then that equals mgh2. Next up, let's plug in the rotational inertia. So 1/2 times 2/5 mr squared. I'm also going to plug in for the angular velocity. So angular velocity equals linear velocity divided by the radius. So v over r squared plus 1/2 mv squared plus mgh1 equals mgh2. So now the mass is in all of the terms now that I plugged in the rotational inertia, so we can cancel it out. Let's do that. By mass. And then I'm also going to cancel out these radii here. We have this r squared, and then we have v divided by r, whole thing squared. So that's going to cancel out. Oh, and then we have a 2 on top and a 2 on bottom there. So now that we canceled everything out, or a bunch of things out, we have 1/5 the velocity squared plus 1/2 times the velocity squared plus gravity times the height of the first hill equals gravity times the height of the second hill. And this is the velocity that we're trying to solve for. So I'm going to move this gh1 to the other side, and then I'm going to combine these terms. So, well, first I'll write it like this: v squared times 1/5 plus 1/2 equals g times height 2 minus height 1. So 1/5 plus 1/2 is 7/10. So we get 7/10 v squared equals gh2 minus h1. And then let's finish solving for the velocity. So we'll divide by 7/10 on both sides and square root both sides. So for the velocity, we get the square root of 10/7 g h2 minus h1. And then let's plug in our numbers. Square root 10 over 7 times 9.8 meters per second squared times, forgot the height, 5.9 minus 4.2. 5.9 meters minus 4.2 meters. This gives us an initial velocity, this minimum initial velocity of 4.9 meters per second. So that's how fast the ball needs to be rolling on top of the first hill in order to make it to the top of the second hill. And the only tricky thing here is that you have to remember that this is rolling motion. So we have to use this kinetic energy equation, you can't just use 1/2 mv squared. You will not get the right answer. Okay, last example. And this one is from this week's practice. So you get, early help or late help, depending on when you watch this, I guess. So we have a projectile that is fired vertically from the Earth's surface with an initial speed of 9.42 kilometers per second. If we neglect atmospheric friction, how far above the Earth's surface will it go? And then again, I added a part. What is the escape velocity of the Earth also? So we can kind of compare that to this initial velocity. So part A, height. Yeah, just start again with conservation of energy. Oh, actually, you know what? I'm going to give you the mass of the Earth, which is 5.97 times 10 to the 24 kilograms. And then the radius of the Earth is 6.38 times 10 to the 6 meters. Okay, now conservation of energy. Initial kinetic, initial potential equals final kinetic plus final potential. If we're looking for the maximum height, that tells us that the velocity at that point is 0. So the final kinetic energy is 0. And then as a reminder, for gravitation, potential energy is negative GMM over R. So that's what we're going to plug in. And this is not rolling motion anymore. So we can just say kinetic energy is 1/2 the mass of our projectile times the initial velocity squared minus G, mass of the Earth, mass of the projectile, over, this is going to be the radius of the Earth is where it starts, because it says from the surface of the Earth. And then this equals negative G, mass of the Earth, mass of the projectile. And here, what we are doing, so you can do this 2 ways. You could just plug in, just put like R or something here and just solve for that value and do, and subtract the radius of the Earth from it later. But I'm going to do it all in one. I don't know if that's better or worse, but that's what we're going to do. So it's radius of the Earth plus this height that we're looking for. Okay, again, we can cancel out the velocity, or sorry, not the velocity, the mass of our projectile, because it's an H term. And I'm also going to divide everything by negative G mass of the Earth, because it's in these 2 terms, the second 2 terms. And if I do this that way, I get it in 1 term. So it's nicer. So we have V squared over 2 negative 2GME, let's see, plus 1 over RE, because we divided by negative GME. And I guess I didn't indicate that was division, divided, not minus. There we go. Equals 1 over the radius of the Earth plus RH. Our H. And then we just want to solve for H. So to do that, I will write out the steps. So we're going to multiply RE plus H on both sides. And then we're going to divide both sides by this whole guy. I'm not going to write it. Well, I can. Divided by negative E squared over 2GME plus 1 over RE. So what we end up with is the radius of the Earth plus H equals 1 divided by negative B squared. Well, actually, yeah, no, it's fine. I'll leave it. Negative B squared 2G mass of the Earth plus 1 over the radius of the Earth. And then we've almost solved for the height. We just need to subtract the radius of the Earth on both sides, so we end up with this. And just real quick, I'm going to swap these terms around, just because I like to kind of tuck the negative into the equation and not, because it's easier to forget it the other way around. So 1 over the radius of the Earth minus v squared over 2g mass of the Earth, and this whole thing minus the radius of the Earth. Okay, that is our equation. Now we can just plug stuff in. 1 divided by 1 over 6.38 times 10 to the 6 meters minus, I forgot, 9.42 kilometers per second. So 9.42 times 10 to the 3 meters per second, whole thing squared, divided by 2 times 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared, times the mass of the Earth, which is 5.97 times 10 to the 24 kilograms. 24 kilograms. That whole thing minus the radius of the Earth. So let's see. No, of course, I didn't do it separately, so we're just gonna get the height is what is it? 1, 2, 3, 6. So 1.555 times 10 to the 6 meters. We can get that in kilometers and get 100 or 1,555 kilometers as the height. So that's the maximum height. Now let's find the escape velocity of the Earth so we can see how it compares to this initial velocity we have. So v escape. Just on the slides it showed, but the escape velocity is the square root of 2 times gravitational constant times mass of whatever you're escaping from, divided by the radius of whatever you're escaping from. So let's plug things in. 2 times 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times 5.97 times 10 to the 24 kilograms divided by 6.38 times 10 to the 6 meters. And that whole thing is square rooted, and we get 11.17 kilometers per second. If you plug that in with meters, which you need to do, it'll actually come out as let's see, this is 1.117 times 10 to the 4 meters per second. But in order to compare it to the initial velocity, which is in kilometers per second, we want to compare. So the initial velocity was the initial 9.42 kilometers per second. So too small, not big enough, which makes sense because we found a maximum height. And if it was big enough, there would be a maximum height. Okay, so those are your examples, and that is your review lecture. Yeah, I hope you had a great quarter. Good luck on all your finals.